In this video we're going to take a look at links 2 and links 3 from the ImaginaryCTF. In the last video we looked at links 1, so this is a continuation of that challenge, and the description says, it turns out there was a bug in how I was handling writing some elements, so I fixed that. Also, I've stopped putting the flag in a global variable because that's probably not a good idea. Double check my implementation one more time for me. And we've been given the binary to download and the server address and port number to connect to. Let's jump straight into Ghidra and take a look at the difference. Okay, so over in Ghidra, I've updated the names of some of the variables and comments and things like that just to make it match what we had last time. And let me just give a quick recap. I would recommend checking out the video for the previous challenge if you haven't looked at it already. But essentially, a developer's created a linked list implementation, and we've got a few sections of the code here where we can add a head node, we can add a tail node, and we can modify a node in the middle. Whenever we add a node, it's going to malloc 72 bytes of data and increase the length of the list. That's for the head node. If we add a node to the tail, it's going to malloc 72 bytes of data. 64 bytes of that is for the actual node, so the data that we can enter into it. And the remaining 8 bytes is going to be a pointer to the next node. So you can see that this one's set up here, so it's setting the 64 bytes into this 72 byte malloc chunk is going to be set to 0. And if you check down here for if we're doing the middle node, you can see then 64 bytes in to the elements data, we're going to write the address of the next node. The problem is, whenever we actually write the data, although we're only supposed to be writing 64 bytes of data because 8 bytes are reserved for the address of the next element, the write data function takes in 100 bytes, so it should only be taking 64 bytes off us. That's how much data we should be able to write to the node, and it's taking 100, which means if we write more than 64, we'll actually be able to control the address that the link points to, that node in the chain points to. So that's generally how this works. In the last challenge we had, in the main function or the menu function, we had the flag being loaded into a global variable. So in order to exploit it, what we could do is add an item to the list. Let me go back to list. We would add an item to the list, and then we would overwrite the link at the end of that entry to point to the flag rather than pointing to the next element in the list. And that means whenever we go to view the list, it's going to loop through each element in the list, and it's going to check what does this element point to, and it'll see whenever it gets to one of them, rather than pointing to the next element in the list, it actually points to the flag, and then it's just going to go ahead and print out that flag for us. So that's how we solved the last challenge. I did mention last time that we had this viewTime function, and I thought that was going to be the goal to solve the challenge would be call system bin.sh. The problem that we ran into was that date is read-only, so it's in the read-only section, which means we can't overwrite that with bin.sh, and I wasn't able to find a way around that. But now that the flag has been removed from the program, we have to find a way around this. This is the only route to a solution that I can think of. So let's see how we can do that. So before we talk about how we're going to approach this, let us just go and review how we can debug the program and analyze what's actually happening on the heap whenever we create these elements. I'm going to open up GDB-PwnDbg and links 2. Let's go in here, let's run the program, and we can view the list, we can add an element to the list, we can view time. So I'm going to say we want to write an element to the list. We'll add a head node, and let me just put this, I'll put chunk 0. There we go, that's been added. So let's hit Control and C, and then let's check the heap. And if we do that, we'll see that we've been allocated this chunk. So we have our top chunk. You'll notice that each time we allocate a new chunk, it's going to take some data from this top chunk. So we'll keep an eye on that. But essentially we've been allocated this chunk, it's 51 in hex, so we have it's actually 80 bytes. And then the 1 is a flag to indicate that the previous chunk is not free. So if we now check, we can do viz heap chunks if we want to take a look at that, and we'll see we've got a top chunk here, and then we have the chunk that we've just created, and you can see, let's do the heap again. So let's have a look at this. This is our address A0, and we can see here A0, so this is the beginning of our chunk. But our chunk data begins here, so you can see here chunk 0, that was the text that we entered. Right before that we have the header, which has the size, so we can see the 5 is indicating that it's 80 bytes, so 5 times 16 chunk and then the 1 to indicate that the previous chunk is not free. And we know that we have 64 bytes of data, right? So it's a 72 byte chunk. Let's have a look here. This is 72 bytes right here. This is the chunk's data. But because this is a custom linked list implementation, we're not actually supposed to be using that entire 72 bytes. We're only supposed to be using the first 64 bytes, and then the remaining 8 bytes is supposed to be reserved. So this address here should hold the address of the next element of the list. It's set to 0 at the moment because if we go back and have a look, remember when we add a head node, it doesn't actually set up a pointer to the next element. There is no next element to point to, so it's set to 0. Similarly, if we add a tail node, the same thing will happen. So it's going to set the tail node to point to 0. So that means if we go ahead and add another node, let's hit continue, let's do 2. We'll add another node, we'll say this is chunk_1. Control and C. Let's check that again, heap, and now we'll see that we've got 2 chunks here, both the same size. We can have a look again, we can just do viz to have a look at the heap, and now we can see we've got our 2 chunks. And if we have a look now at our first chunk, chunk 0, we'll see that we've still got our data in here, but the last 8 bytes of the malloc chunk, is pointing to 5700, which is actually the data of the next chunk, the next element in the list. So this isn't a feature of malloc or the heap, this is part of the custom linked list implementation. And because the next element is the last one in the list, it's pointing to 0. Also note that the size of the top chunk has decreased because we've allocated another chunk from the top chunk to this chunk 1. And again, we can do the same thing. Let's do continue, let's do another node, and we'll write chunk 2. We'll hit Control and C. We'll check the heap, and we'll see we've now got 3 chunks. We can do viz and see that we've got 3 chunks here, and the top chunk has decreased in size again. Now let's try out of interest, let's modify one of the chunks. Let's go back to our add chunk option, and we'll do, let's change the 1, and I'm just going to put here new chunks, we know which one it is. We'll hit Control and C. We don't need to check the heap again, that's going to be the same. What we want to check is the viz heap chunks. And you'll see that this has been modified. So nothing has particularly changed, this is still pointing to the next link in the list. The only thing that's changed is the data in that element. Now one thing I want to just demonstrate as well, let me open up a PwnTools script where we do something very similar. We just create 3 chunks on, or 3 elements of the list, and then we're going to overwrite the second element in the list, so index 1. We're going to overwrite that, and we're going to provide 64 bytes of data. So you can see here hacked as a string. That's going to overwrite the actual data at the beginning, and then we're writing all the way up to 64 bytes in, where should be the address of the next element of the list, and then we'll provide a new address. And notice here that I have 0x51, so I just want to show what happens if we don't have that. Let's do this. We've got a breakpoint here set up at write data, which means using this template we can just do Python exploit GDB. It's going to open up a new GDB window for us. Okay. It's had some problems there. Let me go back to the code. The reason it had some problems is I have this set up view time. So we know that we're going to be calling system. The problem is if we want to access elements from the global offset table, if we try to access the entry in the global offset table before system has been called, it won't yet be populated with the actual address from Lib-C, which is why I have that there. The problem is if we have that there, it causes some issues with GDB, so I'm just going to take that out for now. It's not actually particularly important for what I want to demonstrate. Let's do that again. We will hit a breakpoint this time in write data, that's great. So again, we could do our usual stuff. We could have a look at the heap. There's our top chunk, let's hit continue. Let's do the same again. We've got our first chunk has been added, so we'll hit continue. Same again. There's our second chunk. Continue. Third chunk. And now we're going to overwrite one of the chunks, so we'll hit continue again. I'm going to hit Control and C. Let me do viz again. And notice that we've lost one of the chunks. We have our chunk 0, we have our second chunk, we've lost our third chunk, and we've lost the top chunk. which is not good. This is currently pointing to, let's have a look. Let me unhex this. Okay, so that's currently pointing to hacked, which it should be, which is right here. But we've lost our last chunk. Let's try and do it again with ensuring that we actually overwrite with the correct chunk size. So I'm going to put this back in, take out that system call. We'll run it again. I'm going to skip through a bit, so we'll do continue, continue, continue. Let's have a look at the heap. We've got our 3 chunks. We'll hit continue again, Control and C, and then we'll visualize this. And look what we've got now. We've got all of our chunks, and we can see our top chunk as well. Essentially, the issue there would be if we overwrite this and it doesn't know what size the chunk is. The only reason the heap knows where the next chunk is and where the chunk after that is because of this size field. So if this size is changed, the heap's going to go and it's going to look here, and if I change that to, let's say, 61, it's going to go through this chunk and it's going to look and find out where is the next chunk at. But it's going to think it's 61 away, well, 60 away, that's 6 times 16 bytes away. And it's going to go there and it's going to expect the next chunk to begin, and it's basically going to set all of those chunks out of order. It's going to break the link, so it doesn't know where to find the start of the next chunk. It doesn't know where the current chunk ends and where the next chunk begins, should I say. So that's just something worth bearing in mind. That can cause some issues if we don't preserve the structure of the heap. So what is our attack plan? Well, you've heard me mention the global offset table a couple of times, and if you've seen some of the Pwn challenge videos I've done before on buffer overflow exploits and format string exploits, a common practice is to overwrite elements in the global offset table. So once the global offset table has been populated with the address, you can see here at the moment the system address is 404030. Essentially, the first time system is called in the program, it's going to go and have a look what's the actual address of system in Lib-C, because it's going to be different on everybody's system depending on the Lib-C version, and it's going to return the address, and then every time system is called after that, it knows, okay, we know what the address of system is in Lib-C, just go straight to it. The issue is if we populate that element in the global offset table and then are able to overwrite it with something else, so we can have a look here. Let's do checksec --file, or what's it called, links to. So partial rel-row, if full rel-row was enabled, it would mean we're not able to overwrite elements of the global offset table. Because partial rel-row is enabled, it means we'll be able to do that. So if we were able to overwrite, let's say, just one of these other Lib-C functions with the address of system, and then have a look, where is that function called? So let's go, for example, here's scanf. So if we were to replace scanf with system, can we ensure that bin.sh is passed to system? So can we get bin.sh in the RDI register? We'll have a look at scanf and we'll see what's moved into the RDI is this .data section address, and the .data section, it's the read-only data section, so we can't actually overwrite that, which means even if we could replace this with system, we're not going to be able to get bin.sh in there. So we essentially need to go through and look at each function, so each Lib-C function like puts, like printf, etc., and see which one can we replace and ensure that we control the RDI. It also needs to be something that's not going to break the program as well. So let's say that scanf would have worked, but you have multiple scanf calls throughout the program. If one of the scanf calls you're able to provide bin.sh as a string, that's great, but if you have loads of other scanf calls which are going to cause the program to crash because you've replaced them with system, then that's not going to work. What we ideally would like to find, well, there's a couple of options. We could either find a section of the program that we can write data to, for example the .bss section. We could provide, let's say, this dead address 404090, and we could write the bin.sh string here. And then if we're able to find some way of getting the dead variable, getting that address into the RDI register, it'll be ready for a system call. That's one option. Another option would be to try and find a way to leak the bin.sh string from Lib-C. Or we know that we can write data to elements in the list, so if we can write bin.sh to the stack and then leak that address, we could also supply that. So there's a few different ways we could do it, but there's an even better way, which is to find a function which takes in the user input as a char pointer. And we were just looking at one right there, it's write data. If we have a look at write data, it takes in the element, which is the new node which is being added to the list or modified, and it takes in user data as a parameter. So you've got here fgets, and you can see here the param1 is a char pointer. So the char pointer, it comes in here, it's moved to rbp plus local 20 on the stack, and then it's moved from there to the rax, and then the rax is moved to the RDI right before this fgets call. So if we were to replace the fgets call with system, and we were to provide the bin.sh string as a parameter to write the data to the node, it's going to get down here, it's going to call system, and then bin.sh if that's the string we provide. So our plan of attack is, we'll add a few nodes to the list, add a few elements to the list, and then we'll overflow one of those elements to ensure that it points to the global offset table address for fgets rather than the next element of the list. And then whenever we try to modify the next node, instead of modifying the data of the next node, it's going to modify the data at global offset table.fgets. And we're going to provide the global offset table.system address as our parameter. All we need to do then is modify a node and pass bin.sh as the string, and it should call system bin.sh. So let me copy over a new PwnTools script and let's try this out. I've added a commented out section here to call GDB.attach, and this was because of the system call. So remember that if we call system, we're not going to be able to attach GDB using this traditional method of GDB.debug, which means these breakpoints and stuff here aren't going to work. Another way we can do it is using GDB.attach, so we'll run through all this stuff first and then we'll attach GDB to the process. The only problem is we won't be able to access things like heap or viz heap chunks and things that we were doing earlier whenever we do that, but we'll still be able to do some other stuff, so you might just need to swap between for debugging. To talk through the code again, we're adding 3 elements to the list. We modify the middle element, and we're going to supply the bin.sh string, and then we're going to pad all the way up to the address of the next element in the list, and we're going to replace the address with the global offset table.fgets address, and then we're also going to put in that header as well, so it knows what the size of the chunk is and that the previous chunk is not free, and that'll keep the heap intact. And then we're going to send system, so we're actually going to overwrite the second element, so we're making the last element point to the global offset table.fgets address, and then we're going to write over that with the global offset table.system address. And then we'll need to try to modify an element one more time. We'll modify the element where we wrote the bin.sh string, and that will hopefully then call system bin.sh and give us a shell. Alright, so I'm going to comment this out. I'm going to uncomment this so we can set up a breakpoint. No, I'll leave that as it is. We don't need to set up a breakpoint. Let us just try and run through that. We'll hit a breakpoint here. We've got a breakpoint at read. Okay, so it's just waiting for our input here actually. Let me hit Control and C, and let's have a look and see our global offset table. You can see here fgets is pointing to system at GOT. And we've got the address here of system as well, so you can take a copy of that and check and make sure, look, that is system in our Lib-C library, so it's got that all correct. Notice if I was to go back now and do this again, let's comment out the first call to time, so we're not actually going to populate system in the global offset table. If we do that again and hit Control and C, check the global offset table, it's still pointing to system, but there's no address there. It's just got this address, so it doesn't actually have the address of the Lib-C system function. So that's why that's important. Let me go back and enable that again. we'll run through. Actually, what I'm going to do now is write element to the list. Let's try and do option 1, and let's have a look. It's not hit a breakpoint. We've got a seg fault. Let's go and have a look here. Seg fault, and this is a seg fault here in system at GOT. But everything looks good. We've got our bin.sh string in the RDI as it should be, and we've got system in the RIP as it should be. So really this should be calling system bin.sh and giving us a shell. I actually got a little bit stuck at this point, so I spoke with the support team at iCTF, and they'd mentioned that this was due to stack alignment. So we've got an 8 at the end of the RSP here whenever the system function call is made. So this issue is described in the ROP Emporium guide as the move apps issue. It says if you're seg faulting on move apps instruction in buffered vf printf or do system in the x64 challenges, make sure the stack is 16-byte aligned before returning to glib-C functions such as printf or system. Some versions of glib-C use a move apps instruction to move data onto the stack in certain functions. The 64-bit calling convention requires the stack to be 16-byte aligned before a call instruction, but this is easily violated during ROP chain execution. So essentially, whenever we're making ROP chains, this comes up quite a lot, and what we normally do is find a return instruction. So we'll go and do something like ropper -- file links, and we'll go and find an instruction like this, grab the address of it, and just add that into our ROP chain. But we don't have control of the stack here, so what can we do? Well, another thing we can potentially do is return not to system directly, but skip the first instruction or 2 instructions of system. Let me go back here. So if we were to, rather than going for this push RAX, if we were to go for the next instruction in system, that should resolve the alignment issue. So the problem is, if we go back to our script, if we just try to put in here +1 and say that we want to skip the first instruction, it's not going to work. And the reason being, if we have a look at our global offset table, what's going to happen here is if at the moment we're providing the address 404030, if we do +1, it's going to provide 404031. So we're essentially going to be setting the address, and we're going to be skipping the first byte of the system address, and we're going to be overflowing and taking a byte from the printf address as well. So that doesn't work. What we would essentially need to do is find out what the actual address of system is. So if we were to leak the Lib-C system address and find out, as we did previously, let me have a look, can I just do x system? Here's our address of system. Now if we do, let me do disassemble. If we were to provide an extra a +1 or a +3 or something here, we can essentially specify which instruction we want to start at. So we would need to go and find the actual address rather than a pointer to what should be holding the address. So this doesn't actually require too much of a change. We can already leak addresses. We know that because we essentially did that with our flag, right? In our previous challenge, we provided the address of the flag and leaked the flag. So if we provide the address of the global offset table system address, it's going to leak whatever is held in that location, and what's being held in that location is the actual address of system in Lib-C. So let me go and take a copy of the final solve script for this one. I'm going to paste this in here. You can see that I've actually just got this set to system. We can do system +1. I'll change that to system +1. I actually found out that after getting this working, if we actually find the actual address of system, it doesn't matter about the stack alignment, and we'll be able to test that out in a second as well. So let me just talk through the differences anyway. All of this stuff up here is the same. What we have here is we've just got an extra bit of code which is going to leak the Lib-C system address, so we are providing the system address here as the link to the next element, and then here we're going to go and view the list, and we're going to extract that system address from the list, and that's going to be what we'll use instead. And then we just carry on as we did previously, so we'll overwrite fgets with system, and then we'll try to get a shell. Let me save that, let me close that down. Let's do this again. We run through that and we have now got a shell, which is great. Let's go and debug it though and see what's going on. So I'm going to copy over that GDB attach again. Remember, we have to use this because we're calling system at the beginning. Unless somebody knows the way, let me know if there's a way that we can use GDB-debug and still access those heap commands and stuff, because that would be cool. But if not, we'll set this up here. I'm going to set up a breakpoint this time because we want to go and have a better look at this. Let's do break at write data. I'm going to take this out. We'll just go into interactive. We'll run that. We'll hit our breakpoint. I'm going to hit continue. Oh, wrong button. Hit continue. And we're going to go and write an element to the list. We'll select the option 1 because that's where our bint.sh string is. And now we'll hit this breakpoint again because it's going into write data. I'm going to step through this, and let's step through. We want to get down to where our system call is, which is this fgets call. Remember, we can do our GOT and make sure that everything's looking okay. Has the fgets option been replaced with system? It has. It's been replaced with system plus 1, which is what we specified. You can see here it's ending with a 1 instead of a 0. And let us now step again. Next, next, next. We get down to fgets, which is actually system. And if we look at our RSP, notice it's not ending with an 8 anymore. So this is now in line before the call to system, which is why we're not going to have any issues getting a shell. As I mentioned though, if we actually go back and just take out that 1, and we'll try it again. We hit our breakpoint. I'm going to hit continue again. Let's go in here, write element 1. We hit our breakpoint, and again we can step through here until we get to our fgets call. And again, everything's in line, so it's now going to system instead of system plus 1. Again, we can confirm that. Looking at the global offset table, it's pointing to system, ending with a 0 instead of a 1. And yeah, this works as well, so I'm not too sure exactly what that was about. Let's now just try to get a shell on the remote server. I'm going to take out this GDB script, and I'm going to uncomment this stuff. Let's run it. Let's do remote. Let's take a copy of the server address and the port number. We paste that in. It runs through. Notice when it's running through as well, so we call our system first to make sure that populates. We leak out our global offset table address somewhere. There it is here, system. So that's been leaked out. And now, if we try to ls, we can see we've got a flag, so we can just do cat flag.txt. And there's our flag for links 2. And now on to links 3, which says, and now you guys are exploiting my view time feature that I put there solely for your convenience. Fine, then no more time for you. And we've been given the link to the binary. I'm not going to open this one up in Ghidra. Essentially, it's the same as the one that we've been looking at. The only difference is we don't have this view time function, which also means we don't have the system in the global offset table. So we can't just leak this address. We can't just call system. However, if you've done some pwn challenges before, if you've done some buffer overflows and returned to Lib-C, you'll know that if we leak any one of these Lib-C functions, we can find our way back to the base of Lib-C, and from there we can find our way to any other function in Lib-C we like, or to strings in Lib-C, so for example the bint.sh string. So it shouldn't be too much of a problem for us. Instead of leaking libc.system, we can leak libc.putchar or libc.puts or libc.printf. We'll have a look at the address that's leaked, and based on the offset of it, based on the values, the nibbles or whatever at the end, we'll be able to find out what version of Lib-C that belongs to, and then we'll be able to calculate our offsets to other functions from there. So let me just jump straight over to the code. We've got a Python script here. It's pretty much the same as the last one. I've set this log level to info just to reduce some of the output, and we're going to loop through. Instead of leaking out the system address, we're going to leak out puts, but you could leak out anything you want. And let me just comment this stuff out for now actually. You can see here I've got this libc.rip address. Let's open that up. You can use libc.rip. There's also libc.bluecat.me, I think. although this one seems to be more reliable these days. And essentially we can put in here a function name and the address that we leaked, and it'll give us some possible Lib-C libraries and the offsets of different functions within them. If we supply more than one symbol name and more than one address, we'll be more likely to narrow down the search options so that we've got less options to check. So let's try and run this first of all. I'm going to just leak out. We could do this against our local system, but we already know what version of Lib-C we're running. We can just go and look at our Lib-C library, but let's check it anyway. Python exploit, it leaks out our puts address, so I could go here and say to the Lib-C database, the symbol is called puts, and I want you to find any Lib-C library that could be potentially running on the system. And then we can either download the Lib-C library, we could download them all actually and loop through until one of them works, or we can just go and manually put in these offsets. I normally like to automate things quite a lot, so I'll typically load Lib-C in as a binary here, and then I'll update the Lib-C address, and then it means you don't have to hard code values, but I'm not going to do that for this one. If you want to see more of that, go and check out the binary exploitation playlist I put together, or have a look at some of the other PwnCTF challenges I've done. For this one, we're just going to manually put in these offsets. So that's our local system. That's no good to us. We want to find out what Lib-C is running on the remote server. So we'll run this again. We'll do remote. We'll paste that in. It's going to come back and tell us that the puts address is this one. So we'll take a copy of that. We'll go back to Lib-C database. We'll update this and find. Again, we've got quite a few different ones here, so we might want to go and leak something else and try to narrow it down. What if I put in here fgets, and then we'll do that again. We've leaked out, okay, that's not the fgets address. Let's try printf. Okay, that looks better. I guess fgets wasn't populated or something. Okay, so printf, find, and now we've narrowed it down even more, so we've only got two Lib-C libraries that we need to try. I think I actually left a comment to say which one it is in the script. It's the 3.5 one, so let's save a little bit more time. Oh, they're both 3.5. It's 3.5 Ubuntu 3. Although they might be the same offset. Sometimes the offsets are the same. Although they aren't for this one. Okay, so anyway, this is the puts offset. So if we go back, and let me just change that back to puts. Now if we go back here and say Lib-C, the base of the Lib-C binary is going to be puts minus that offset that we've just extracted, and then system from there is going to be right here. So system is this far away from the base, so we'll add that, and now we have the address of system, and now we just proceed with the rest as normal. So let's just comment this, uncomment this, let us run that again. It runs through, we get our puts address, we get our system address, and we get a shell. There's no end of file, which is always a good sign. So we'll do cat flag.txt, and there's the flag for links 3. So just to recap what we've done, we've dealt with 3 challenges, links 1, links 2, and links 3. All were using a vulnerable links list implementation, and each challenge had a patch done, so each time the vulnerability from the previous challenge had been fixed. In the first one, we were able to modify one of the addresses of the next nodes in the list to point to the flag and then just leak that out by viewing the list. In the second challenge, we weren't able to do that. The flag wasn't loaded into the program. So instead, we overwrote the fgets address in the global offset table with the address of system, and then we passed bin sh as a string to the write data function, which meant that whenever it called fgets with our parameter, it actually called system with our parameter and gave us a shell. In links 3, we didn't have access to the system address, so we just had to leak out another Lib-C address, identify what version was running on the remote server, and then update our offsets accordingly. So I hope you've enjoyed this video. I learned quite a lot going through it because I'm not too good with Heap stuff, and it just meant that I had to go through and kind of debug what the layout of things were and how things were working on that front. I will put a write-up for each one of these challenges on my GitHub. So normally I just make a video, but I'm going to start doing some write-ups as well. You can see I did a write-up for this use after free challenge from Pico a couple of weeks ago. So I'm going to add a very detailed write-up for all 3 of these challenges on GitHub, and the solve scripts and stuff will be there as well. They're not up at the moment because this month of challenges hasn't actually ended yet. So today's the 1st of July, which means a new month of challenges will start. So every day there'll be a new challenge, and at the end of the month write-ups are allowed, and there's, you know, winners based on who did the best over the month. So I'd highly advise you check it out anyway. I think there's some great quality challenges on here. The Discord is set up well to offer support if you get stuck on a challenge, and they're also running a CTF in 2 weeks' time, I believe. Let me check, does it actually mention here somewhere? Homepage. It doesn't mention. Next challenge is in 5 hours and 20 minutes. I'm pretty sure it's in like 2 weeks. It'll probably be on CTF time or something. If not, go and join the Discord and you'll be able to find out more in there. Alright, thanks for watching. Any questions or comments, leave them down below. Thanks.